哈喽，教授，为什么没有人来？
是啊，为什么没有人来？我也很奇怪。这个，哎呀，最起码应该来吧？
对啊，现在越来越少了，怎么办？
哎，还好，这个很正常，很正常。这个3、4个、4、5个人都是非常正常的情况。这个课可能还好，以后你们上别的课的话，就是如果你们看别的读别的书的话，可能人会更少，可能就那么2、3个人轮流讲，这很正常。
适应就好。
主要学的人不够多嘛。我们这个平时这种东西的话，确实学的人这个感兴趣的人可能也少一些。然后你将来就是越窄的话，学的越窄的话，那感兴趣的人肯定就越少，这也没办法。
是。这本书什么时候才能读完？我感觉遥遥无期了已经。
哎呀，不用担心，这个书的话，基本上你们把第3章学完之后，就是你们如果不是学拓扑的话就可以了，就差不多了，基本上。当然最好还是能把学到第8章，这是最好的。
第8章。
对，学到第8章，然后第2部分就不要用这个书学就可以了。第2部分的话，如果你们对这个代数拓扑感兴趣的话，我们可以换一本书再继续学。
我感觉我可能撑不到那个时候。
没有关系，你们现在基本上已经学了一半了，对不对？这个你看一看，总共300来页，对吧？总共你们需要学的300来页，现在都快学到150页了，那基本上就是已经过半了。虽然一直是在第1章。Hello。
Hi, Zora.
Hello.
Yeah, we are discussing about although we are still on the first chapter, but just as you said, our target is to finish chapter 8 eventually. So we already made half of it. So yeah, we did pretty good job.
Yeah.
So the next chapters are significantly shorter than the first 2 chapters, is it so?
Well, the thing is, the first chapter is very fundamental, which is why it's actually pretty long. And to me, I think if you are not in this topology area, and if you try to learn, for instance, in the future, like geometry or analysis, then I think the chapter 2 and chapter 3 are the most important thing. And beyond that, it's something more topology, but I think in the future you may forget this kind of thing after chapter 3. But still, it's very if you got the point, it will be very interesting. You will think it's very interesting eventually.
Shall we wait Aya for a couple of minutes?
Maybe we should add her on the group so that to make sure she's not. Well, I think she will be here, right? She just asked in the group. Hey, I think we should start, right? It's already 15, and it seems
Okay.
that I didn't reply to us.
Yes. So I will start. By the way, today is still 3 hours, right? Or 1 hour and a half.
Well, we only have, other than me, you only 2 guys, so you can discuss about it.
Okay.
I have not prepared for today, so an hour and a half I think will be good.
Okay. Yeah. Okay, 1 hour and a half. It's good for me. Maybe I'm tired. Okay. I will share my screen first. Can you see this?
Yeah.
Okay, I think so. Today we'll introduce some more about the metric topology. So first, let's discuss the relation of the metric topology to the concepts we introduced. First is the subspaces of the metric spaces. So the textbook says if A is a subspace of the topological space X and D is a metric for X, then the restriction of D to A product A is the metric for the topology of A. So I searched for the definition of the restriction, and some notations are kind of complex, so I just copied that here. So maybe it's like seems very hard to understand, and it is also hard for me. So I may write some tips, maybe translate the language here. So how it behaves in the metric space context. So basically, if we have a metric space M, sorry, maybe right here, here, X, D, D is metric from XX to R. So this is the D. So the restriction D, maybe we denote it as the A, is from A to R, where A is a subset of X. So what we need to show is that this new metric space, ADA, it is a subspace, metric subspace of this one, XD. And we need to show that DA is actually a metric on A. Does that make sense?
Yep.
Okay. So do you have ideas? Only you.
Sorry, I don't think I understand your question.
Okay. So basically, what we have is that we have a metric space defined before is M, right?
Mm-hmm. Yep.
And the D is defined as this. And now we have a subspace metric space. It is like this A is a subset of X, and DA is this one. We need to show that DA is actually a metric on A.
Okay, now I have to think. So the first two properties of a metric, they follow from the fact that dx is symmetric on x cross x, right?
Yes, right.
And for the triangle inequality, do we need to go any further, or we can say that it follows directly from the fact that the triangle inequality holds some x?
Actually, those three conditions are like all can be like satisfied by this D. We can only like consider some relationships between dA and D and cannot like go to very details about the conditions of a dA. Okay, so maybe I will tell you that is not hard, but kind of very hard to explain in language. So as we show here, for any, where is my point? Oh, okay, sorry. For any xy in A, we have dA right? If we given 2 points x and y. And since D is metric, so dA in this case satisfied all these three conditions, and dA is also a metric. So that's basically the proof, and it's just like some application of definitions. Is yeah. So for other concepts, the other topologies, some are metrical and others are not. For example, R and positive integers. Oh, here. For R, basically we define like A minus B, the absolute value. For positive integers, I think we can also define this way maybe. And Hausdorff axiom, it is satisfied by every metric topology. So this is not very hard to say. Maybe I will visualize it. It's not very clear. So basically, the definition of Hausdorff axiom tells us that if we have two distinct points, x and y, and we can always find two disjoint neighborhoods, right? So suppose we have this metric space XD, and we just let epsilon equals half of the metric between x and y. Then basically the triangle inequality implies that these to neighborhoods BD x epsilon, BD y epsilon are disjoint. So that's because if we suppose that there is a point here that shows that these two neighborhoods are not disjoint, we basically will have suppose this point is Z. This is by triangle inequality. But on the other hand, since Z is in the epsilon ball BDX, this ball, so it's less epsilon, and this less than epsilon. So basically, this less than 2 epsilon, which equals to dxy, right? So that gives a contradiction. So that cannot be true. So these two neighborhoods are actually strong here. So for the product topologies, things go a little bit harder than before. So if it is generally said that the countable products of metrical spaces are metrizable. It is a very similar proof to the theorem we discussed last time, is theorem 20.5. I think it's kind of a little bit hard. So maybe I will just tell you how to show this. So in the theorem 20.5, what we show is basically like the countable products of the R, right? So in this case, we need to show it's the metrizable spaces. Maybe it's not R. So maybe we can rewrite this in another way. Suppose we have a we define this bound metric as this. And on a metrizable spaces, I will just use a random notation, maybe M. And okay, we have 2 points, X and Y. So we can also define the metric dxy this way. Then D induces the product topology on maybe R M omega. So this is the condition we have in this case. So the first part is very easy to show. Aya told us before is to show that dxy is a metric. Those 3 conditions are satisfied. So I will not show here. Maybe I will just go the harder part. We need to show that the product topology and the metric topology basically are the same. So let's first go this way. Suppose we have a open set U in the metric topology, and we basically have a point in this set, and we find an open set V in the product topology. We want to show that X belongs to V and is subset of U. So for this metric topology, basically we can always find the epsilon ball, right? So we find this epsilon ball, and we set the metric is epsilon, and we choose n large enough that 1 over n is less than epsilon. So for the metric topology, maybe something different. We select a basic element of this product topology, and upon my understanding, I think it can define this way. Where for each vi is open, and for in this app, for I equals alpha 1, alpha 2, alpha n, and ui is a vi equals m for other I, right? So and for each vi, we can define it as some epsilon ball here. This is D. So we want to show that V is a subset of U. Maybe clear here. So upon my understanding, if we visualize this part, like if we have like a ball U, and we have another, like we find a ball in it is the BD. It's the basic element of this topology, and it lies inside this U. So if we find some V like has the same epsilon, but it actually lies inside it. So we basically want to show this. So how to show this? Maybe I will clear this. So if we have a point y in this the product topology, we basically have the bounded metric if I larger or equal to 1. That's because this one is always less or equal to 1, right? So this one is of course less than this 1 over n. So, and we can conclude that so for this part, since this set can have infinity many terms, so this term actually represents this infinity terms. Since we cannot like make sure whether how they behave, so we just use this inequality to like represent them. And this, of course, less than epsilon, since we choose this at first. Also, for this one, sorry, I think I have enough. Okay, I will continue this. Also, for this one, if we know that this one is less than epsilon. Sorry, I don't know why. Okay, let's continue. So, so for this part, if we know that it's in the epsilon ball, it is in V, it's of course less than epsilon, right? Since we define V as some epsilon ball, BD, like X epsilon, we of course know this distance less than epsilon. So all of this also less than epsilon. So all of this, of course, less than epsilon. We know that this D is also less than epsilon. That means this Y must belongs to BD. Must in this form. So that means V is a subset of this and also a subset of U. This is one of the directions. Does that make sense? Okay, no questions. Okay, then I will show the other direction here. Oh, it seems that I cannot erase this. Oh, that sucks. Okay, maybe I will write in other white parts. Use a different colors, maybe. So in another direction, in the textbook, the author use a different V and U, but I think it's kind of confusing, so I just maintain it. So if we still have this V is a basis element of the product topology, but in this part we do not have some restrictions on VI because in this part VI is something like larger, and we want to show this metric topology is a subset of V. So basically, for each VI, we can write it as some epsilon ball, like with the metric epsilon I. So in this direction, our main task is to find some, like the minimum of this metric, so that we can make sure that all of this in either directions of this either dimensions of U is all in this Vi, all in this way, right? So so one of the most important steps is to find the minimum of the epsilon. Like to hold the inequality, we basically choose the minimum of epsilon I, like divide by I. So if we select the minimum of these numbers, we define it as epsilon. And we can show that X that's basically because if we have a point, Y is where is the basis element of the metric topology U, it is BDX epsilon. And for all I, we can show that this inequality must hold. Right, since we can just multiply by I on both sides. So that gives us that Y belongs to this Vi. So we successfully show this. And on the whole picture, we show that these two basis elements just the same. So these two topologies are the same. Any questions?
I think we're good. We can move on to the next slide.
Okay. So here comes our main part for this section. Basically, we discussed two parts. First, we connect the familiar epsilon delta definition of continuity and to this metric spaces. And other is also for the convergent sequence definition of continuity. These are very common in the analysis. The other part is we also introduced two additional methods for constructing continuous functions. So first, we discuss this epsilon delta definition of continuity. Basically, it says if f is a function like from x to y, and x and y, if x and y are metrizable with matrix dx and dy, so the continuity of f is just equivalent to the requirement that given x, which is belong to x, and given epsilon larger than 0, there is
I can't hear you, Zikang.
Me neither.
Given epsilon, they're always
Okay.
equal.
I cannot hear you again. Hello, Zikang. Bad signal.
I think he's not in the Zoom meeting right now.
No. He just lost his signal, I guess. Just I think we just need to wait for a second.
Oh, sorry. I just noticed that my internet connection collapsed, so I will reconnect.
Yeah, that's okay.
Okay. So I just introduced this theorem, and I just state again. Any questions here? Okay, if not, any ideas to prove it? Maybe I will draw something first.
Hey, Zikang, I think I cannot really see your screen, so are you sharing?
Really?
No.
Oh, okay, I will try to share it. Okay. Does that work?
Yeah.
Yeah.
Mm-hmm.
So Zikang, are you talking, or because I cannot hear anything?
I'm not talking.
You're just drawing, right?
Point.
Okay.
Yeah,
Okay.
I want to give some time to like think about this proof. Or if no ideas, I will just show how to prove it.
Okay. Yeah, that's totally fine.
So the first like in the first direction, it's like if there's an open set on Y, I think, and its inverse image on X would be open as well.
Yes,
And
right.
both of those sets would be symbols with wait, sorry, this is a bad way to say it. So if the open set V on Y is a ball which is I'm on my phone and I cannot write, like dy of f of x and epsilon, and this we can just label its equivalent open set on X, which is the inverse image of V is the ball dx x and delta, something like that.
Yes, I think like you are close to this, the first direction, like from continuous to this epsilon delta definition. So basically, like as you said, if we have an open set in this Y, we select it as this ball, since it contains fx, and we find this inverse in X, is of course open in X, right? Because f is continuous. And also, of course, it also contains X. So in this open set, we can always find an epsilon, find a ball. Right? With some metric, like we just set it as delta here to satisfy this proof. So that's basically gives the first direction of this proof. So for any epsilon larger than 0, there always exists a delta epsilon, such that if x in this ball, that means the xy less than epsilon, and we can get dy fx x fy less than epsilon. That basically means this b fx. This point is in this ball, right? So for other direction, from epsilon delta definition to the continuity of f, a little bit more complicated, but also not hard to say. So basically, if we want to show a function is continuous, we first have an open set in Y, right? And we want to show that this inverse is open in X, right? So in this subchapter, the basic strategy we use is like to always find a point. If we have a point in this set, we want to show that there is an open set contains X that is a subset of this. And this gives us that this is open. That's because this is an open set. And for any point X, we can always find this open set. So this is also open. So that's basically our thoughts in mind. So how to find this open set for any X? So that's because maybe I will erase this first. We know that fx is an element of this open set, and so there is an epsilon ball b fx centered at fx and contained in this open set, right? So by the epsilon delta condition. That's basically gives us this relation. That may be hard to understand at first glance, but if you think a little bit, it really makes sense. So that's because at my first understanding is that since we from this we can always get this, right? That means it can be like roughly seen like subset notation here. That means this set may be larger than this set. So that means if we draw it, if we have some set, maybe be here fx epsilon, this bx delta is contained in this. So because for any epsilon, we can always find a dot delta. So that's basically gives us this open set U. This U contains X and is a subset of this F inverse V, if we set V as this. So let's finish the proof. Any questions here?
So sorry, I just get a little bit, I just forgot. Did you show the equivalency, which means two sides? I forgot. This is one side,
yes,
right?
I first introduced from continuous to the epsilon delta definition, and this is from epsilon delta definition to the continuous. Sorry, makes the confusion. Maybe my presentation is not very clear.
It's okay. Yeah, you just erase everything. So which is why I just forgot
Yeah.
which part you already finished. Yeah.
Yeah,
that's
maybe
okay.
Yeah. So any other questions?
No.
Okay, next. So here comes another definition of the continuity. So another very like typical definition of the continuity is the convergent sequences. And in the topology, like we would define the convergent before. I will just remind you how it looks like. Basically, it says like corresponding to each neighborhood U of X, there is a positive integer n, such that xn belongs to U for all n larger or equal than the bigger. So if you try to visualize it in a real line, it's like if we have a point X and we have for each neighborhood U, we can draw this way, larger or smaller. We can always find many like xn if n larger or equal to some positive integer n. Okay, so that's the definition of the convergent. So this lemma basically says if X is a topological space and A is a subset of X, if there is a sequence of points of A convergent to X, then X belongs to the closure of A, and the converse holds if X is matrix. Also, for this one, we need to show two directions. First is from the converge back to X belongs to closure of A. And second is X belongs to closure of A and A is matrixable, or X is matrix. To converge. So first, this first direction is not hard to say. If you can remember, one of the theorems we discussed is the theorem in the subchapter 17.4, I think. It's about the closure, some equivalent relation of closure and another statement. Any ideas for this direction? Okay. So I will basically tell you how this theorem works, how the previous theorem works. So basically, that gives us that if X belongs to a closure of A, it is equivalent to that for each neighborhood, like we denote it as U of X, it always intersects some point other than X. Right? So if we give the converging condition, that means that for every neighborhood of X, we can always find this intersection point, right? Which is belongs to A, X and belongs to A, right? So that basically gives us that X belongs to the closure of A. Is that okay? So for the other direction, if we know that X belongs to closure of A and X is matrixable, basically we can use the concept of metric. It's kind of like the distance. If you learn the analysis course, the distance is always like very widely used. So we can use this concept here. So we can use this real line to show how this works. Like suppose X belongs to this A closure, and for each positive like Xn, like n, we can choose a ball. In the real lines, basically it gives us many intervals, right? Like a sequence of intervals. So from very larger to very smaller. So we have these like sets of intervals. And then for each of these interval, we can always choose some xn in it, right? So that basically gives us that every neighborhood of U contains some x, contains some xn other than x, right? So in like an interval language, it's like if we have a neighborhood U. This U always contains some BD in this ball, right? If we choose 1 over n less than epsilon. Is that okay? Any questions here? Okay, if not, maybe I will just go next.
Well, just quick comments about this. So you can see that this kind of this lemma just tell us something. When we learn the topology, we always try to understand the topological space as a metric space. However, this lemma just tell us, okay, sometimes it's just in our imagination, right? The real topological space may be worse than we thought. For instance, this kind of convergence may not have any sequence that converges to this point, right? So then a very natural question is, well, if you do not have this kind of materializable property of the space, do you have any counterexample to show that this the converse does not hold?
Okay, maybe I will think about it for a little
Yeah, this
moment.
may not be an easy problem, so you can try to think about it, and then you can see that why when we define the topological space, we cannot always assume that there is a metric on this space, right? It will be totally different if we do not have this kind of assumption space, but it's still something makes sense in topology.
Mm-hmm. How about some like, does that 3-point set work? I don't think.
No, it's fine. I mean, this kind of topology, you can see that later. Well, as long as you have this topology satisfies so-called the first continuity axioms, it should be okay, right? Later in this book. So, but then if you want to find some kind of topology that is not satisfy the first countable axioms, which sometimes we call it T0. This is also kind of separation lemma stuff, separation property of a topology. Then it's this kind of space is it's not really nice. But I think we can discuss this kind of thing when we discuss about the exercise, not now. Yeah, because now then you will get stuck.
Okay.
It's not very, it's not very easy because it's different from our intuition, which is why it's well, not so easy.
Yes.
Mhm.
Yes.
Yeah, we can discuss it later when we discuss about the exercise and more examples. Okay.
Okay. Sure. Okay, I will go next. Here, we have some like new concepts. One is the countable basis at a point, x some point. Another is the first countability axiom. A space X is said to have a countable basis at a point X if there is a countable collection UN, where n belongs to the positive numbers of neighborhoods of X such that any neighborhood U of X contains at least one of the sets UN. So the space X has these like properties set to satisfy the first countability axiom. So this one, from this one, like we can rewrite what we proved in the theorem in the lemma, the sequence lemma. That means, so we can rewrite this and what I said, like the sequence of the intervals, maybe not very rigorous. Like to some sections of sets. So you can see that actually we did the same thing. If we have a point X and for any like the neighborhood of this X, we can always find some Bn if Bn equals this, right? This is the real line. And like we can say it in a more abstract way. We can use this expression. It's just some like intersections of many sets. These sets like are countable collection. Okay. Any questions? Okay, I will go next. I think I left one theorem. I don't know why my slides on my computer always omit one slide I made. It's actually a bug. I don't know why. The other like, okay, I will write it here maybe. The other part, like one of these theorems using this lemma says like that. If we have a function if we have function f from x to y, and if the function is continuous, then for every convergence sequence, like fxn to x in x, the sequence fn convergence to fx, the converse holds if fx is metric. It's very like kind of similar to the lemma before, right? So here, basically, we have two things. If from continuous to given xn to x, then fxn here A is fx. Sorry, make confusion here. Fxn to fx, and here is from this convergent condition to continuous. Any ideas? Yeah, from this continuous, we can get that if phi is the neighborhood of fx, then this one is the neighborhood of x, right? So this what remind you maybe. Okay, I will just show you. So that means that this is the neighborhood of x, right? So for n larger or equal to n, xn must belong to this neighborhood, right? So fxn belongs to V. Is that okay?
Yes.
Okay. So let's do the other direction. If we know this convergence sequence condition, we want to show f is continuous. So basically, we can apply what we proved in the lemma. By the way, like a hint, for this continuous proof, we use this equivalent condition to show. I think Dora gives this relation in her presentation. So if we have A is a subset of X and FA closure is a subset of FA closure, that means F is continuous. Is that okay? Okay, I will show you how to prove this. Maybe I will erase this as it's messy currently. So basically we want to show this is a subset of the closure of FA, right? So if X is a point of FA closure, then there is a sequence Xn of points of A convergent to X. Right? That's the lemma we proved before. Right? Xn converges to X and Xn belongs to A. And we use the condition that X is matrixable. So from this, Fn, by our assumption, we know that Fxn converges to Fx, right? And we know that Fxn belongs to Fa. This is from this, right? Oh, sorry. So Fx belongs to the closure of Fa by our preceding lemma, right? We know that this converge hold. So Fx belongs to this closure. So that basically gives this conclusion. Any questions? Oh.
It's a very neat proof. I like it.
Ah, okay. Okay, maybe we'll go next.
Yep.
Yeah. This next is how to construct the continuous functions. So first we give a lemma. The addition, subtraction, and multiplication operations are continuous functions from R cross R into R, and the quotient operation is a continuous function from R cross R subtract this zero set into R. This I want to give this as an exercise, but we only have one person here, so can you like think about this and try doing it maybe? So I will, this is actually the exercise 12 in the textbook, and the author gives us some hint. And I maybe formalize this in another, like in a more clear way. So if we want to show that first, the addition condition holds, that basically means if we give a function like fxy to basically equals x plus y. And we want to show this function is continuous. So the hint author gives is that if we given an epsilon and we let delta equals epsilon over 2, also he gives an inequality is that yeah, this D is the metric in the real line. So that means we can write it as x minus x minus. So one of the confusing question here is how to like define a metric in this R cross R. Okay. Any ideas?
I'm just writing in my notebook and trying to figure it out. Like I
Okay,
think
great.
I need to think.
Any ideas? Want to say something? Okay, maybe I will just show how to prove it. So for the addition, as we are given here, we have this function and like epsilon delta and this hint, right? So we just try to organize it like in order. So do you remember what we proved at first at the theorem 21.1? So it basically tells us that the epsilon delta like we can apply this epsilon delta language like to prove it. So if we let delta equals epsilon divided by 2 and this is the metric in R cross R. And the D right here, and it basically equals to this, and so maybe a little stark here. So we basically define the metric as the max of x minus x0, y minus. So it so that gives us the proof. Any questions?
I think I got it.
Okay. Okay, no questions. Let's do the multiplication. It's a little bit complicated, but the basic strategy is the same. So suppose we have a function here. Suppose we have function gxy equals xy. And the author, the hint, gives the hint is that if we have a point f if we have x0, y0, and epsilon between 0 and 1, that 3 delta equals epsilon over this. This and also inequality. Yeah, this inequality is very good. And from this, we can easily see how to use this delta to show the final inequality. Okay, suppose we still define the metric in R cross R as the max of x minus x0, y minus y0. And it basically is the delta. Yeah.
Sorry, how do you get the first inequality, which is given a second in the book? Like, I'm just trying to go from the metric between xy and x0, like y0, to the inequality.
You mean this metric? How to define?
Like, how do you go for this one?
On this part? On this part? Yeah, this basically the author's hint.
Yeah, that's my question. I'm
Yeah.
probably missing a few algebra operations because it's.
Yeah. I got that. So, you mean how to get this inequality? Yeah. So if you do some operations on that, just like multiply this x0 in it, you can find that x0y minus x0y0 and plus. Okay, so we just ignore this first. Okay, we just basically it's larger or equal to this, right? Maybe it's it's not clear. But term by term is this, right? And there are 3 terms, right? If we all plug these 3 in one absolute value sign, it's the triangle inequality, right? It is larger or equal to this, basically, right? And you can try to cancel some terms, and you find magic happens. Like this one, this one, this one, this. What left is x, y, minus x. Right? It's just it's d.
Yeah. Thank you. I got it now.
So the interesting thing is that why we write it this way. That's because every term has some absolute value to show the metric in the real line, right? It's basically less or equal to the delta we define for each y minus y0 or x minus x0, right? So basically we can just do some operations and get this. So that's very close to this one, right? Okay, so we just close to the answer here actually. It is like epsilon over 3 and it's less than epsilon. Is that okay? Actually, I don't know why it is 3 here. Maybe I do some calculations wrong. I don't know here.
It doesn't matter. You can take epsilon over 100, right? Or epsilon over 10,000, right? It doesn't matter here, but well, he just want to leave some rooms for it. This is very usual in the proof of analysis.
I see.
Yeah. Because eventually you want it to be less than epsilon, right? Yeah, but eventually, if you put it epsilon there, then it seems that there's no room to improve. So this is something may not be good in analysis.
Yes, thank you. So any questions? Yeah, I noticed that the time is 8:44 in China. So maybe I will just finish this proof of this lemma and we finish this session today. Okay.
Okay.
Or we just continue maybe.
I'm fine with both. It's 3:44 in the afternoon here, so it's okay for me.
Okay. If no more questions, I'll continue.
So the plan, the current plan, if I'm understanding it correctly, you will continue and finish the quotient operation, right? And leave the theorems next time, or you want to finish it this time?
I think since we only have 2 people here, maybe next time.
Okay, so yeah, so are you going to finish the quotient operation?
Yes. Yeah. Actually,
okay.
I have 2 questions in the textbook. Basically, the author outlined how to prove this lemma, and he gives 4 questions, and we just solve 2 questions, and there are 2 left. So that basically gives how to show the subtraction and quotient operation. And yeah, I will finish this part. So the third question is, show the operation of taking reciprocals is a continuous map from R minus 0 to R. That basically means if we define function this way, we want to show this function is continuous. And the hint is show the inverse image of this function is open. So if we are given an open interval AB, and we want to show this inverse image is open as well. And this gives us that H is continuous by the definition. So we need to consider 5 cases here, actually. A negative, B positive, A positive, B positive, A negative, B negative, A 0, B positive, or A negative, B 0. Basically, it's not hard to say.
Oh, wait. There, I'm sorry. I think okay. There's a very detailed things about the notation. So you take the inverse of the reciprocal map, right?
Yes.
But for the reciprocal map, you can see that the domain is actually from R minus 0, right?
Yes.
And the range is also R minus 0, right?
Range is R, I think.
Can you but yeah. You can also take it, right?
Yeah.
You can also take the range as R minus 0, right?
Yeah. But
so which means there are 2 situations there you don't really need to count.
These 2 cases?
Yeah, I think if you don't really need to say, well, if A is negative, B is positive, or only this case you may not need to consider, right? If A is negative, B is positive.
I think it's like, for example, gives like this case. Maybe.
But it's okay. Yeah, it doesn't really matter here. Yeah.
I think
if
so,
if you consider the range as a whole R, then it's fine. Yeah. Anyway.
I see. Yeah. Right. Right. So I think it's not hard to say, right? We'll take this one as an example. If we have a negative B positive, to have an intuitive like picture, if we set A as -1, B as 1, or maybe 2, so we can see the reciprocals. It's like this. Right? The inverse image. So it's of course open. So similar cases for other conditions. So maybe you can check yourself. Yeah. So from these 3 cases, that gives us, from this case, we can show the quotient operation is actually a continuous function. That's because if we have a quotient function k behaves like this, maybe x times minus y to the power of -1 or x minus 1 y, we can write it as a composition. Of some continuous functions we proved before. This G is multiplication, and this H is the reciprocals. Right? The K is the composition of two continuous functions, so it's continuous. So for the subtraction, I think we can do the same way. If we define some function like to take the negative of it, just, and we prove it by show the inverse image is also open. The subtraction operation is just like the composition of two functions here. F is the plus operation, and this is to take the negative. So it's also continuous. Okay, let's finish the proof. So any questions so far? Okay, if not, maybe we'll finish today's seminar.
Yeah,
And I think next time is Tuesday, right?
Is that Tuesday or Monday? I forgot.
I think it's Tuesday, maybe. Yeah.
Yeah. Well, I think we decided some days, but whatever. Yeah. But before that, well, let me make a remark about this here. Okay.
Okay.
So that you for this one, you can see that if you try to do it very careful, then you'll find that the proof of this kind of lemma is actually almost the same as when you try to prove in calculus class the limit of summation of two functions is just as the limit of the sum of the limit, and the limit of the subtraction is a sum of the limit. Is a subtraction of the limit. The limit of the production is the multiplication of the limit, and the limit of the quotient is also the division of the limit. Okay.
Mm-hmm.
I hope you can think about it. Well, why these two are actually the same thing? You try to do this, why is the same thing? And the why is actually not the same thing in the general topological space. Okay, but it's the same. It's the same thing in metric space, and especially in R. Taking the limit and you prove how well the limit of this kind of operations can keep the limit. It's also the same as this kind of operations considered as map is continuous. Okay, it's actually the same as it's the same thing in R. Prove these two things are the same. Okay.
Do we define the limits here? I don't.
Yeah. Well, but here you can see that we consider the continuous function defined by this continuous, well, by this open set, not by a limit, right? So which is why they are the same, right? But in R, in this Euclidean space R, the limit way to consider as to define the continuous map is the same as the open set way to define the open, right?
Oh, right.
Yeah, so which is why when you are able to prove this in the language of limit, then it's okay. It's of course okay to prove they're continuous, right? They are continuous in whatever definition. Mm-hmm. But in general, this is also, well, this could also be true, right, in the metric space. And another remark I would like to say, another comment is, well, when we try to study this metric space and metric topology, you may see that if you have a topological space and you have a metric, then it's actually this topological space is measurable. It's actually a pretty strong condition on this topological space. And then you discuss, okay, this space will satisfy all our imagination about about what we learn in calculus class or in analysis class, which is I think is pretty good. And also the reason why we study it in this way, or why we are interested in topology, is very simple. It's simply because we try to take out those key features about these spaces. Like if you study in R, then you have all these kind of good properties. Then what if we study some properties that are in not very good space, not really in R? For instance, in the future when you learn the geometry, what if we study this kind of thing in some surface, in some manifold, right? And in this kind of thing, you may not, this kind of manifold or surfaces may not be as good as R, may not be as good as Euclidean space. Then what kind of property should still hold in this when you try to study the calculus on this kind of space? Like in this space, if you are already defined a metric on this space, you still have the continuity of this kind of operations, this lemma, or the next theorem just tell you, okay, this is fine, right? But this is not trivial when you try to see it in the future, when you try to see it when you learn the geometry. Why is that still the same, for instance? Yeah. And this is also, in general, this is also very important, which is when you're trying to make a weak assumption about, well, for instance, your reference space or some in your assumption, you weaken your assumption, then are you still able to prove your theorems? This is actually a very good way to do some research, okay? You already see some result, for instance, in R. Then are you able to prove this kind of result in some other space? Then if you want to do that, if you want to do a study about that, then you have to be very careful about the proof and see what kind of property you really need in the proof, right? For instance, in this kind of property, this operations are continuous, or this kind of sequence lemma. Of course, they are true in R, but if you want to do some research about this property or about this lemma, about these theorems, then you may ask yourself, it is true in R, but is it still be provable, or is it still be true in some other spaces? If it is, and you write it down, then this could be a research project. If it is not, then you find some counterexample. This could also be a research project, right? And in general, the research on math, a lot of papers in math are this kind of papers. You try to make it a general assumption, or you try to release some assumptions and try to prove it, okay? So this is why it's kind of useful.
Yes, but I think in my learning experience, I don't learn much about other spaces other than R and Euclidean spaces.
Yes, because this in this section, it's about the metric, okay? In this section, it's about metric, so everything you can imagine is in R. However, when you, at the very beginning, try to learn this kind of topology, right? Then you try to learn it in this topological space. This is actually a very key difference between this Munkres book, this Munkres book, and others, some other system of topology books. In this Munkres books, he starts with the general topological space. So he trying to avoid asking you, okay, what happens in R? Okay, what happens if you have a metric? If you already have a metric in this space, and then what happens? So he tried to take the most abstract way to introduce you what is topology. And then there is another system. I think I also read this kind of textbook as well, which is he start with the metric space, which is basically he start with the R. Okay, and then start with it, and eventually take the abstract definition of topology. After he, in R, he introduced what is open, what is closed, what is compact, what is connected. He tried to take the abstract definition. Okay, both way works. Both way works, and there are also in both way you can find a lot of textbooks introduce topology in this way. Okay, and I would say when you try to learn in this Munkres book, you already learned this in your analysis course, what is open set, or open interval, or closed interval. Okay, so I think you already got this intuition, and then you try to learn in this way. I think it might be better for you to understand what is topology. Okay, but whatever. At this moment, you may think, okay, everything is based on R. But later, when you see more examples, you'll find that, okay, maybe sometimes we need to consider something different from R.
Yes.
I forgot where it is, but I guess maybe in the next section, probably maybe in next chapter, there's a very interesting examples. Maybe you will see that later. There's very interesting examples, which is so-called topologist sine curve, which is a sine curve, sine 1 over x. Okay, everybody knows this function, sine 1 over x. This function is oscillate, especially near the origin, right?
Yes.
And then you try to study what is the topological property of this curve. Then you find that it's totally different from R. Okay, and in that case, you will see, okay, why we want to study this topology in some other way. Or even later, maybe in this chapter, you can see that in this exercise, he also introduced you some examples, and for instance, on a sphere. Okay, so sphere is almost the same as R. It's just something that is not really R, because it's actually a bounded set, right? Rn or R3 or R2 is something unbounded, but a sphere is actually a bounded set. Okay, and then you will see that if you try to study something in a sphere, it will be different from R, but there are still some properties on R that could be satisfied in the sphere. Okay. So this is why sometimes you can try to consider the property in R, that's totally fine, but sometimes you have to use the original definition in topology to study something else. Okay?
Okay, I got that. Thank you.
So maybe we should stop here. Yeah, it's already late. So that's about when shall we meet, but I think it's on our WeChat group, and there might be, maybe it's Tuesday. Yeah, maybe it's Tuesday. I forgot.
I will confirm it on the WeChat group.
Okay, that's great. Okay.
Okay. Okay, thank you, Professor.
Yeah, thank you. That's a very good talk. Thank you.
Okay.
Well, you did a lot of preparation. Yeah.
Okay, see you.
Okay, see you next week.
See you next week.
Mm-hmm.